Hi, in this video, we will talk about maxima and minima, okay? So first, I would like to introduce the absolute maximum minimum, or some of the textbook, they name it global maximum minimum then, okay? So to the absolute max or min, let's see. We would like to let C be a number in the domain of D of a function f, then f of C, the output, right, at x equal to C, is the absolute maximum value of f on D if f of C greater than or equal to f of x for x in D. Okay, so in this case, the situation that we may have. Right now, I have a functions, okay? Okay. So maybe in this case, the domain that I have is actually from A to B, okay? And then in this case, what happened is actually you will see that f of C, okay, is the biggest output, okay, the largest output that I have. So therefore, in this case, this f of C is the absolute maximum values then, okay? Or we may have some situations. So in this case, okay, again, the domain is actually this one is from A to B, okay? Then now, in this case, you will see that here, the f of B is the largest output, okay, within this domain. So therefore, in this case, f of B is the absolute maximum value then, okay? So therefore, again, when we talk about the absolute maximum or the minimum values, we need to look at the endpoint as well, okay? And absolute minimum values of f on D if f of C less than or equal to f of x for all x in D, okay? So then in this case, of course, you will see that to our first example, then f of A, it will be the absolute minimum then, okay? Because this is the smallest, okay, output values that we have within these functions. Okay. And also, of course, in this case, is also f of A, right, will be the smallest, okay? Okay, then now, the next one is, if we want to look at the local maximum or minimum, or some of the textbook, they call it relative, okay? Relative max and min, okay? Okay. But again, to me, I like to use a local maximum and minimum, okay? Okay, so the number f of C is the local maximum values of f if f of C greater than or equal to f of x when x is near C. So this is the kind of like the big difference between the absolute maximum and the relative maximum. So in this case, it's actually tell you that you have a functions, okay? And then if you have the C values here, then what they're looking for is they're looking for when the X is near C, okay? So you will see that when it's near C, meaning when you have it to the left and to the right. So in this case, within these small chunk, okay, small portion of the functions, we are looking for the biggest, okay, output or the largest output within this small, okay, area right here. So therefore, again, in this case, of course, in this case, this f of C is the local maximum now, okay? So therefore, again, in some sense, if I want to find the local maximum, meaning I need to have the function that changing from increasing to decreasing, then this point right here is my local maximum. Okay. On the other hand, a local minimum of f if f of c less than or equal to f of x when x is near c. Okay. So in this case, then maybe we could consider that this point D, okay, again, within this portion, okay, this area of the functions, then D to the left and to the right, of D, okay. So within this area right here, then f of D is the smallest, okay, output values. So therefore, in this case, f of D is the local minimum, okay, in this case, okay. So therefore, again, when we talk about the local maximum and minimum, we are not consider the endpoint, okay. Okay, so now sometime if the problem asks you to find the extremum, okay, or absolute extremum, what they're looking for the absolute max or minimum. The local extremum, they're looking for the local maximum or the minimum then. Okay. So then let us look at the following example, okay. So in this case, okay, the domain that I have is actually, it will be from here to here, okay. So this will be the domain, okay, of these functions. Within this domain, f of d is the biggest output values. So therefore, we will have the absolute maximum, okay, values will be f of d. And in this case, f of a, okay, is the smallest output values that we have within this domain here. So therefore, f of a will be the absolute minimum then. And how about this one right here? Okay, so you will see that as x equal to b, okay, then within this small area, this small interval right here, f of b is the biggest output, okay. So therefore, in this case, f of b will be the local maximum now, okay. And again, it is changing from increasing to decreasing, okay. Of course, another one is also f of d is the local maximum as well, okay. But you will see that f of d, it is also the absolute maximum, okay. Then in this case, this f of c will be the local minimum, okay. Again, it's changing from decreasing to increasing. And of course, f of e is also the local minimum, right? Then the next theorems I would like to talk about is the extreme value theorems. If f is continuous on a closed interval AB, okay, it must be a closed interval. Then f is thin and absolute maximum values f of c and also absolute minimum f of d as some number c and d in AB. Okay, so if you have a closed interval, essentially is guaranteed that you will be able to find the absolute maximum and minimum. Okay, just like look at the first example. This is my absolute maximum. This is my absolute minimum. And then in this case, this will be my absolute max. This is my absolute min. Okay. And sometimes you may have, okay, have like the same values, okay, of the absolute maximum at different input, okay. That happened too, okay. So in this case, when I talk about the absolute max, I will have f of c sub 1 and f of c sub 2 then, okay. And in this case, of course, my absolute minimum values is f of d. Okay, let's say this one. Okay, so now, okay, so we would like to look at these definitions here. Okay, so a critical numbers of a function f is a number c in the domain of f such that f prime of c equal to 0 or f prime of c does not exceed. Okay, so we talk about critical numbers when we have it on our first package already. Okay, and then remember when we mentioned f prime of c equal to 0, meaning this c right here is related to the local maximum or the minimum. Okay, and then when f prime of c does not exceed, meaning we either have a sharp corner or we may have a gap or a jump. Okay, or sometimes we may have a like vertical asymptotes. That's mean vertical tangent line, right? Okay. Okay. But right now, because we are talking about, that means most of the time is the function f that we are talking about is continuous functions. So usually we omit this case right here. Okay. Okay, so with these critical numbers, because we have f prime of z equal to 0, or sometimes we have f prime of c does not exist. So we have different name, okay, to these two types of critical numbers. Okay, if the number c is stationary values, if f prime of z equal to 0. So if I have f prime of z equal to 0, then this c is what we call a stationary value. Okay, and c f of c is a stationary point. The number c is singular values if f prime of c does not exist. Okay, and c f of c is called singular point. Okay, okay. Then now let's get back to the example that we have here. Okay, so in this case, okay, then we will be able to say that again, my critical numbers. Okay, it will be x equal to b, c, d, and e. Okay, those are my critical numbers. But under these critical numbers, we have two types, right? One is f prime of c equal to 0. This is what we call the, again, stationary. Okay. Another type will be f prime of c does not exceed. Okay. Then this one is what we call the singular. Okay. So then in this case, okay, for the stationary, then we will have x is equal to b, d, and e. Okay. For the singular is when x is equal to c then. Okay. Okay, so another three number. If f has a local maximum or minimum at c, then c is a critical numbers. Okay, just like what we mentioned it here then. And now let us try to again work on the following example then. Okay, so to this example, I would like to locate and classify all extremum, okay, meaning absolute maximum, minimum, local maximum, and minimum. Also, I would like to locate any stationary points and singular point, meaning we are looking for the critical numbers, right? Work with the critical numbers. Okay, and notice that closed intervals contain endpoints. but open interval that do not. Okay, so just remember this. Okay, so now then let us look at our first example. Okay, maybe let us look at this function f right here. Okay, so what is the domain? We will see that to this function, the domain is in between -8 and 6. Okay, it is continuous function within this interval then. Okay. Okay, so again, based on the extreme value theorems, okay, then I will be able to find the absolute maximum and minimum, okay, to these functions. Okay. So then now, first, I'm looking for the local maximum point, okay, so in this case, I will see that these two, okay, are the local maximum points, which is -3, 2, and the 0.45. And now the local minimum points, I have two of them, okay? There's two right here. So it will be -5, -6, and -1, -3. Then now, my absolute maximum point, okay, well, this give me the largest output, right? That means in this case right here, my absolute maximum point, it will be -8, 6. And now my absolute minimum, this one give me the smallest output, right? So then my absolute minimum is -5, -6 now. Okay. And then now I'm looking for the stationary point. Okay, now remember stationary point is related to f prime of c equal to 0. Okay. So then in this case, my stationary point, I will have, let's see, okay. So this one, and this one. Okay. And my singular point, probably this is my singular point because it's related to f prime of c does not exceed. Okay, so which is the sharp corner that we have. Okay, so then the singular point is -3, 2 now. Okay. Then of course, if we have a closed interval, meaning in this case, I will have two endpoints, -8, 6, and 6, 2. Okay. And how many critical numbers I have? Of course, I will have 1, 2, 3, and 4. Okay, so those are x equal to -5, -3, -1, and 4. Okay, so now then try to see if you could work on the next example now. Okay. Now, when you look at this example right here, be careful about this arrow, meaning the function basically it will come like continuous this way. So in this case, the domain of this function is from -6 to infinity then. Okay. Okay. And now let's see our example now. Okay. My local maximum point, okay, so in this case, probably I have two of them. So they are -3, 5, and 3, 3. And local minimum, I have two of them. It will be 1, -2, and 5, -7. Okay. So then how about my absolute maximum points? Okay. Now you will see that in this case, what happened, the function basically, when I notice this arrow, meaning the function basically is keep going up, right? So then you know that if it's keep going up, meaning there's no point there, right? Because it's getting bigger and bigger. Okay, so therefore in this case, I will say that, oh, actually I have no maximum, the absolute maximum then. Okay. Then how about the absolute minimum points? So in this case, I have two of them. Okay, so then they are -6, -7, 5, and -7. Okay. Then how many stationary points? Okay, so in this case, probably this one and this one right here. So I have two of them is 1, -2, and 5, -7. How many singular? Again, I think that I have two of them. So they are -3, 5, and 3, 3. Okay. And I only have one endpoint, which is -6, -7. Okay. And how many critical numbers? Okay, of course, I have four of them. X equal to -3, 1, 3, and 5. Okay. Okay. Now, one thing about this is from time to time, the problem may not ask you to find points if they're looking for values, right? For example, if they ask you to find the absolute minimum values, okay? So in this case, what they're looking for, they're looking for the output value. So therefore, in this case, it will be -7. That means they're looking for the y value. Okay, if they're looking for the absolute minimum values. Okay, or same thing with the local maximum values, right? So again, in this case, my local maximum values, I actually have two. It is 5 and 3 then. Okay. Okay. Then now, the next theorem is that the values of the derivative at a local extremum, okay, is that let's f be a function with a continuous graph. If a local extremum of f occur at c, f of c, then f prime of c equal to 0 or f prime of c does not exist. Okay. And then you will see that here, I actually have continuous functions. Then do you see that in this case, my local extremum, okay, meaning these 4 points right here, is either is f prime of c equal to 0, this one and this one. And to f prime of c does not exist, it will be the one carry the singular, right? That the singular points. Okay. Okay. However, the converse is not true. That's it. If f prime of c equal to 0 and f prime of c is undefined or does not exist, then a local extremum is not guaranteed to occur at c f of c. Okay. Is there an example to do that? Okay. Let's see. One of the example maybe I could think of is how about f of x equal to x to the power 3. Okay. So in this case, f prime of x equal to 3x squared. Okay. And now I would like to, again, I would like to see if I could set the f prime of x equal to 3x squared equal to 0. Okay. Then I would like to find out what c is, right? So of course, in this case, x is equal to 0. So this is actually is when x equal to 0, okay, the derivative is equal to 0 then. Okay. However, we know that the graph of x to the power 3 okay, you will see that x equal to 0, in this case right here, is not maximum or minimum. Okay. So therefore, be careful about this theorem then. Okay, so then now, okay, so maybe I stop it here, okay? And then the next video, we are going to work on the example then.